Okay. So last class, what we were talking about, we were still on the topic of electrical fields and electrical fields of objects with a certain geometry. And we were the last example or situation we were talking about was a charged disk. And we had gotten up to this point where we had gotten to the representation of the integral that we had to solve to get the mathematical expression for the electrical field of a charged disk at a certain distance. Okay, now I'm not going to go in detail on the rest of the slides. The next 2 or 3 slides are the demonstration as to how to solve that integral. The procedure is in the slides, but the explanation of the procedure is also in the corresponding YouTube video. So remember that we've got the recordings of the classes, but I recorded 3 separate videos for each of the explanations for each of these situations that are standalone. Okay, so the procedure to solve this integral has to do with trigonometric substitution as well. And again, the procedure is here. I'm not going to go into detail with it. I'm not going to ask you to solve integrals in the exams. I'm just doing the demonstration as to how we got to the expressions, but the complete procedure is there. And again, it's using trigonometric substitution. And in the end, we get to this expression that we have down here. So this expression here is the one that defines an electrical field for a charged disk. Yes.
It's 2 pi k. What's the other side?
Oh, the other is sigma. It's this symbol right here. And remembering that, because that can be a question, that should be a question in the exam. In the case of a linear distribution, we used lambda. Lambda was charge divided by length. In the case of something that has a surface, like a disk, we use sigma, and sigma is charge divided by area. What's the surface distribution? And so it's sigma.
So lambda is for?
Lambda would be for a length. So for example, a line or a circumference or anything like that, where the charge is distributed along the length. So it's coulombs by meter. And sigma is used for something that has a surface. So a disk, a square, or anything where the charge is distributed along a surface. There's another representation that we could also use. We're not necessarily going to have to use it, but I'm just going to mention it here. There's another one also that's called rho, where it's charge distributed by volume, assuming that we had a sphere or a cube or something that had volume. We're not going to be really needing to reference that now, but I'm just mentioning because it exists. Rho.
So sorry for asking again.
No,
Lambda for what? And sigma for what?
Lambda is for a linear distribution of charge. So lambda is, I'm going to write it here, it's coulombs. Remembering that the units are coulombs. It's coulombs per meter. Coulombs per meter. And sigma is for an area distribution. It's coulombs divided by meter squared.
And sigma is for a surface. Something like
For a surface, correct.
So like lambda line, sigma surface. Like
Exactly. So lambda is a line. It's how the charge, and all of these, we're using these constants because it's a uniform distribution. All of the charges distributed uniformly along a line, which is lambda, or along a surface for sigma. And that's what that symbol is over there. Yeah, remember, if any of my writing isn't clear, then please nicely let me know. Okay. And so let's do some examples as to how we would use this expression. And I'm gonna need you guys to do calculations, so turn down for what? Well, the three houses, please help out with the calculations and let's verify the calculations, okay? So we have them. So the situation now is we've got a disk. And that disk has a certain radius. And there's a point that's located from the center of the disk, and we want to see what the electrical field is at that point that's coming out. That's a certain distance from the center of the disk. And there's two problems associated with that. So the first one is we've got a disk that's a 1 centimeter radius disk that has a uniform charge of 3 microcoulombs. And we want to see what the electrical field is at a distance that is 1 meter from the center of the disk, perpendicular to the center of the disk. Remember at home, if you have any questions or the audio goes out or whatever, let me know. Just open the mic and let me know, because sometimes you guys write it in the chat, but I don't want to put the chat in the screen because sometimes some of you need to go to the bathroom and I don't necessarily want that to be public. So just open your mics if you want to ask a question or have any comments. Okay, so let's identify the elements we have. That's the first thing we need to do to address this problem. So what information do we have there that's going to be useful?
The radius.
Radius, we have the radius, which is 1 centimeter, and we want to represent that as meters, so it's 0.01 meters, correct. What else do we have there? The distance, and the distance is represented by what variable? Z. So the distance from the center of the ring is Z, and that's 1 meter. Somebody said the charge. The charge is 3 microcoulombs, and remembering that this is 3 times 10 to the minus 6 coulombs.
The K constant.
The K, we know that K is the electrical constant. We're always going to be using that one. So we're always going to remember that K is 9 times 10 to the 9 newtons. Newtons, meters, newtons, coulombs. Newtons, meters, coulombs. And what else are we missing that we've also got this that we would need to find?
What's the name? Alpha?
Sigma. Sigma. So we need to find sigma, and sigma we can calculate. So sigma is going to be equal to the total charge divided by the area that it covers. And so we know that the total charge is 3 times 10 to the minus 6 coulombs. And the area, what area would we consider?
Oh, the circle or this?
In this case, the disk, and we need the area of the disk. How do we calculate the area of the disk? It would be pi multiplied by the radius squared. In this case, the radius is 0.01 meters squared. And so please calculate sigma and give me that value.
I have a question.
Yes, go ahead. Yes, sir.
This is a different problem that the one that we did the perimeter.
Yes.
Like it's calculated differently.
Okay.
What I mean.
Yes, the problem where we did the perimeter, yes, sir, it's because that is a ring. Okay, it's a ring. So it is linear first off, because it's just the outer part of a circle. This situation is different because it's not just the outer part of the circle, it's the whole circle that has a charge. Okay, so the previous one that we did, we used the expression for the electrical field of a charged ring. Right now, we're doing it for a charged disk. And again, the difference between one and the other one is that the ring is just the outer part. The disk is going to be the whole circle, including the surface. Okay? Does that make sense? Is that clear?
Yes, it's clear. Thank you.
Okay, perfect. Okay. So please do that calculation. Give me some values so we can. Correct.
But I don't know if it's good.
Okay, let's check and we'll validate.
0.00954.
0.00, another zero?
954. Me too.
With what, with 2 zeros or 2? 2. This could have been 9.54 times 10 to the minus 3. That's, or 95.4 to the minus 4, depending on where you put the point. Okay, so a few of you got that one as well?
Yes.
Okay, good. Now we're going to substitute these in the expression over here. And I want you guys to please calculate that as well. It's going to be 2 pi 9 times 10 to the 9. I'm just going to substitute the values right now, just to make it shorter. Sigma, which is 0.0954 multiplied by 1 minus 1 divided by the square root of 1 squared plus 0.01 squared.
Professor, one question. What's the name for the distance again? That symbol?
That's a z. Oh, the distance from the center to the top, that's a z.
Okay.
But the normal.
Just confirm.
normal z. Yes.
The main equation is R elevated
Yes.
Right.
Yes.
and Z.
Yeah, this is. Yeah, I did a screenshot there with the. And here on the screen, it's a bit more fuzzy. It's z squared plus r squared. And it can be the other way around, r squared plus z squared. Square root of that. So let's do that calculation and give me the value. Okay, so please do that calculation. If anybody has the value, give it to me. And we'll check. Don't worry if it's incorrect or not. We'll check
I got
it.
it, but I don't know.
Okay, let's see.
I think it's wrong. 26,971.
26,971 and 16. Okay, let's verify. 0.69. 69. Okay. Okay, let's verify that. That's a good technique. I sometimes use it. I don't know if it's a technique or not, but I use it as a technique sometimes. When I'm gonna do something, I usually say, well, you know what, I'm not really good. I'm not really good at public speaking. I really get very nervous. I'm not sure. And then I nail it. And everybody's like, oh, So he's good. So yeah, that. I don't know if it's a technique or not, but if it is a technique, keep using it. It's good. It's good.
Professor,
Yes.
I have a question. It's
Go ahead,
because
Jeffrey.
you have different values in sigma in the original calculation and when you calculate E.
I missed a zero, right?
Yes.
Okay, good, good. Thank you.
Then I don't have it. It's like this, well,
It would be this, I think probably the value would be the same. It would be,
only like
but-
the point,
yeah,
yes.
0.0954. We missed a zero there. I think that maybe if the calculation is correct, maybe the value is correct, but the point is going to be moved. So let's validate this one here. So please calculate and let me know if we need to change something here.
Right.
Okay.
Me too.
Let's see both of them.
26,919.7.
Yes, that exactly me too.
But the point is still here.
I have a different 100.
Okay, and what did you get?
Wait, you got 26,000.
Yes, I got 53.
I got 269,900.
Alejandra, did you use did you add the other zero in the calculations? Okay. And so
We'll do it
let's
again.
verify that. Let's over at home, do the calculation again. We've got three results that are very similar, around 26,000. So you got 53,000, which is kind of like half. So double check that one. Remember that there's a 2 here. Don't forget the 2 here on this side, everybody. Over at home, what values are you getting? You guys getting?
Too much. Oh, I have.
I got the value that is already on the board.
You have 53,000. So some of you have 53. Let's do the exercise like we did it last time.
I have 53,900.
The same as Alejandra, 26,987.109.
Okay, so let's do this. Let's do this in parts, just to practice. And this exercise to do it in parts is what I call troubleshooting. So first, give me the results of these three products. 2 times pi times 9 times 10 to the 9.
5.65 times 10 to the 10.
5.65 times 10 to the 10. Everybody verify that one. We got the same. Good. Now we're going to do this one multiplied by the 0.00954. So give me the result of these two.
I already have it, but it's very.
It's 5394742.
5.
39.
Well, let's use
I
2.
got it different, but I think it will be
You
the
have
same.
53,942.03.
Oh, it's not with the point, right? It's- So again, 539,000. So let's use one of them and let's verify. So, Dio, give me the value there of these two.
53,942.03.
No, I don't got nothing like that.
Okay.
I got
No?
539832228.5. But I got the same answer as Alejandra.
But again, oh, I see where the competitive is. Again, what we're doing is troubleshooting. So we got different results. We want to check where the calculation might have gone wrong. So we apparently got the first one correct. What I want to verify is those two. So everybody, let's use the same amount of decimals. Let's multiply 5.65 times 10 to the 10 multiplied by 0.00954.
It's 53901.
Yes, I got it.
You were ready.
53901.
0000 4 zeros.
4 zeros.
Yes, I got that too.
Okay. So let's write that one down. So it's in the range of, yeah, because we've got it times 10 to the 10. So, yeah, let's see that again, Andre.
Erase.
Okay.
53901 and 40.
53 million.
1 0 more professor.
4 zeros at the end.
Zeros, okay. 539 million, okay? So it might have been a multiplier there?
What?
It might have been a multiplier there that's different?
No, it's like that.
Oh, is that one? Is that one? Okay. And now let's see this one, this operation here.
No,
There's a
I don't think the radians are different.
He has 26.
I use the same like calculator and it's like I have something totally.
I already put it
We
in
use the
degrees.
calculator, okay.
I have
But the radians and degrees
26,000
shouldn't.
Because we're not using angles.
That's odd.
Maybe they use 3.4
No, you
instead of 5.
No, I used like.
Could be. The other, I don't think, well, no, the other would be the interpretation of pi from the calculator, but that would be odd as well. Let's see the last one. What's the value there of the last calculation? 1 minus 1 divided by the square root?
4.99962 times 10 to the minus 5.
This one here, let's use 4.96.
99. Okay. 999
Okay, so let's leave 4.9 times 10 to the
minus 5.
minus 5. Let's verify that one.
Yeah.
Yeah, we're good.
Um,
Somebody got something different from these two?
no.
Okay.
26,411.
The final calculation.
And yes.
Okay, let's see. The final calculation then would be then E equals, could you say that again?
411.49.
Okay, can we verify if we're getting something in that
Yes.
range?
Yes, correct.
We do? Okay. Again, I'm just trying to go step by step because, again, troubleshooting and debugging.
Oh, I'm still watching the second.
You got something different in the, in
I
which?
don't get that 4.9 times 10 to the minus.
No, you got something different there, Esther?
Me too.
What do you get, Viviana?
26,948.
No, that's for the last value?
Yes.
Okay, if we're in the range of the 26,000, we're okay. The rest of the values could have been affected by the decimals, okay? So if we're in the range of the 26,000, then we're okay. I thought you were mentioning about the square root value. So if we're in the range of the 26,000, we're good. If we're getting something out of that range, then that's fine. We mentioned that since we're working with small values and multipliers, they're going to be very, very sensible of the decimals there, okay? So that's why we could get the 411 or we could get something larger or smaller than that, okay? Okay. Okay. I'm not going to erase it. No, no, no. Just going to change this to take a screenshot. Okay.
O sea, sí, pero no es como que difícil.
Okay, so okay, so I'm gonna just take another screenshot of this. Okay, and I'm gonna jump over to the next. I'm gonna clear the drawings, but again, this is gonna be in the PowerPoint, okay, and in the recording. Okay, okay, so the next part of the exercise is now we've got we found the electrical field. And so what's going to be happening here is that we're going to have, now we're going to place a charge of, we're going to put a negative charge here of -4 microcoulombs. And we know that there's an electrical field there. And so because of that electrical field, we're going to have a force. And that force is going to be an attraction force because the disk has a positive charge. And that force is going to be represented like this. Now, how do I represent the force for an electrical charge if I have an electrical field? Well,
E
Um,
times the
E
charge.
times Q, correct. Very, very well. Very good, Andrea. So it's going to be E times Q. And the value of E that we had was, we're going to use the one we had on the last slide, 2600, 411 point what? Did you write down there?
49.
49, we're going to use that value. And so the force, and again, this is important for the reference in the calculations. We're calculating the magnitude of the force. So again, for exercises where we're calculating force, electrical field, etc., don't substitute the sign of the charge in the calculations because it's misleading. Yes, Lisa?
Professor, I was writing, I didn't pay attention. Why did we put the force equals?
E times Q. Oh, okay.
why
So
is it not-
if we have an electrical field and we place a charge in the electrical field, then the electrical field is going to be equal to force by unit charge. That's an expression.
But what are they asking on the column that?
Oh, they're asking for the force. So we're placing a negative charge. Yeah.
We have to get the field.
So it's the same situation we had before. It's the same disk. It's a point, and we're placing a negative charge there. We want to know the force that's being exerted.
Because that one was like field negative.
And so remember to not substitute the sign there because, and this is important because the next topic we're going to see after the last topic that has to do with electrical potential, we are going to substitute the signs in that, but it's because it's different. In this case, remember that we're working with vectors or vectorial representations. And so signs have meaning. So the sign, if I put the sign, it means that it's going somewhere, the force or the electrical field. So when we do the calculations, we don't use the signs because they can be misleading. The signs are going to help us identify if it's an attraction or repulsion force, and they're going to help us place the forces and the electrical fields in the free body diagram. And so in this case, the force that's being exerted on that charge is going to be 411.49 newtons coulombs multiplied by the charge that in this case is 4 microcoulombs, 4 times 10 to the -6 coulombs. And so this force, the force that's being exerted, please do that calculation.
I got 0.105 newtons, but I don't know.
Me too.
0.105 newtons. Okay. That's the one. Okay. Okay. That wraps up that. That wraps up that section that has to do with electrical fields.
Professor, I have a question.
Yes, go ahead, Anya, please.
There on the problem says that we have to find the force between the ring charge But didn't we
That's a-
calculate the disk charge?
That's a typo. Thank you for that. And yeah, that's a typo. And it has to be, it's the ring, correct. Thank you for that. I need to correct that here on the slide. It is the disk. It's really confusing. Yeah, okay, thank you, Anya. Yep, it's a disk charge. Problem number one.
Yes, thank you.
Okay. Remember that some of your classmates are selling Krispy Kreme donuts? And the good thing about selling Krispy Kreme donuts is that you can eat Krispy Kreme donuts. And Krispy Kreme donuts make people happy.
Today is your last chance, by the way. So
Order now or forever be left without Krispy Kreme donuts.
exactly.
I
You
always
can buy
buy,
them with me, Inya.
Any, because I said that promotion.
it's a competition between Anya and Yusuf. I always buy the boxes and literally I buy the 12 donut box and depending on what hour of the day they give me the box to my home, only about half of those arrive. So if I get the box in the morning and I'm in my office, not teaching class, I'm gonna start eating the donuts and I only get about 6 of them back home. And I mean, I don't recommend anybody to do that, but they're really yummy. Okay. Questions with this one before we jump along to our next topic. Okay. Okay, I'm gonna clear this. Okay, and so the next, we've got we've got 3 topics left before we finish up unit 1, learning module 1, which is, I think, the largest one in the course. And I asked you to research a little bit about these on Friday. It's basically 4 concepts. And the first one is something that's called electric flux. Now, what is electric flux? So the concept of flux anywhere, flux is going to represent, or is going to be kind of a measure of the amount of something that's flowing through a certain area. Is your calculator okay? It seems rugged. It's a rugged calculator. So flux, when we talk about any sort of flux, it means that we have something that's going through a certain surface. And it's important because depending on the amount of thing that's going through the surface, is if we have a lot of flux or less flux. So imagine that you have like a river, okay, and you cut out a square. You have a square of let's say metal, and you put it in the river, and so there's going to be water going through the square because it's a surface, and you could kind of have a measure of how much water is going through the square. That would be the flow of water going through the square. Now imagine that instead of having a square, I use a circumference. So the geometry is different and the surface area is different. So there's going to be a different amount of water going through the circumference. Now imagine that I put a triangle there. Put a triangle. The triangle is going to have a different superficial area. So there's going to be a different amount of water going through that area. So again, sometimes imagining these things with regards to fluids is more useful. Well, now let's imagine that in space, I've got electrical charges. So we all know that electrical charges are going to be generating electrical fields, and we can't see electrical fields, but the electrical field is going to be this thing that's being emanated by the charge. We represent that emanation with lines. And let's say that the strength of the lines represents the strength of the electrical field. So the concept of electrical flux is, okay, I've got electrical charges or an electrical charge that's emanating an electrical field. Depending on where I'm located is how much of that electrical field is going through a particular area, okay? So we know that the further away we are from the charge, the lesser the electrical field is. The closer we are, the closer it is. So we would reason that if we're talking about flux or how much electrical field is going through a certain area, depending on how close we are and how large or small the area is, we could say that that's a proportion of the electrical field or the strength of the electrical field. So the electrical flux is, again, imagine that the electrical field are these lines, and I have a certain surface area, and I want to know how many of those lines are going through that area. And so electrical flux is represented by this Greek symbol here. It's this Greek symbol. And basically the electrical flux is going to be the magnitude of the electrical field that's going through a certain area, but it has to be the electrical field that's perpendicular to the area, okay? Meaning, let's try to think about the river, okay? We've got a river of water flowing from point A to point B. And imagine imagine that I have a square, a metal square. If I want to know how much water is going through per unit area, I'm going to have a different result if I put the square perpendicular to the flow, or if I kind of move it. The amount of water that's going through is going to be the same. Would you agree? But the amount of water per unit area is going to be different. A clear example of this that you've experienced. How many of you have played with a water hose in your lives as children? Okay. Hopefully all of you have, because if you haven't, then sadness. So you played with a water hose. So the water hose has a certain pressure and water is coming out. And what happens when you put your thumb there?
Like faster.
It goes faster, but the amount of water is the same, right? But the amount of water per unit area is different, and that means that under the same pressure, the water is going out quicker. But if you had a bucket, and I don't know how many of you have tried to fill in the bucket by pressing it so it fills in faster. It's not going to fill in faster. The amount of water that's coming out is the same, okay? It's something similar here. Depending on how the area is positioned is how much flux we're going to have. So we always represent the electrical field, but the electrical field that's going perpendicular to the surface area. So that's why in this example that we've got here, we've got a certain electrical field that's going from left to right. So we've got an electrical field that's going from left to right here. Right now, we don't know what's generating the electrical field. We don't care. We just know that there's an electrical field that's going like this. And I place a certain surface here. And the surface has a certain inclination. So the only part of the electrical field that I'm interested in is the one that's perpendicular to the area. So if the electrical field is going this way, then the one that I'm interested in is the one that's going perpendicular to the area. The one that's going along the area, that doesn't have any effect. And so if we're talking about a surface area that's known, the flux is going to be the electrical field multiplied by the area times the cosine, because it's the one that's going to be perpendicular, assuming that the angle is taken from the x-axis. If we have a different surface, a surface that kind of has different parts and different geometries, well, as we know up to this point, what is the normal expression turns into an integral. So if we were to have a surface that has many parts in it, then we would have to integrate the different areas that would have. And that's a more general representation of the electrical flux. That would be the integral of the electrical field along the perpendicular lines of the area. Okay. And so why is it useful to know about electrical flux? Well, because of Gauss's law. And that's the thing about this course, more than any of the other courses you guys have taken in physics. There's a lot of people in this course. There's a lot of historical figures. So right now we've heard of Coulomb's law, and we already knew about Newton. There's a bunch of people and a bunch of laws in this course. So right now we know about Coulomb. And we know about Newton. Now we're going to talk about Gauss. Gauss was another fellow that helped, another fellow that is very important in electricity and magnetism. And there's something called Gauss's law. And this guy Gauss developed this law that is useful to represent different, it's useful to represent different electrical fields for objects that have different volumes and geometries. And basically what Gauss's law says is that the total electrical flux that's going through a certain surface is going to be equal to the total charge that's enclosed within that surface divided by permittivity. And remember that permittivity, which is this E here that we have that we have here on the bottom. Permittivity, which is that E, and remember the relation, permittivity, it permits. It's a measure of how much electrical field can be allowed by a certain medium. So permittivity 0 is the permittivity of vacuum.
What?
Vacuum, vacío. For up to this point, we're always going to be using permittivity 0 because we're going to always be considering that the charges are in vacuum. However, if we want to be very specific, we might say, well, they're not in vacuum, they're in a certain fluid, they're in water. Well, permittivity would be different. Or if they were in a certain environment that had smoke in it or something like that, permittivity would be different. Right now, we're thinking that it's in vacuum, so it's permittivity 0. So the electrical flux is going to be equal to the charge contained within the surface divided by the permittivity. Okay. Okay.
Permittivity was measure of how much electrical flow can be allowed by a fixed
A certain medium.
medium.
A medium or medium. So medium means whatever's around us. Okay, so for example, right now, what's around us is air. And air has a certain permittivity. Vacuum is, remember that vacuum is always going to be the reference. So vacuum is space. There's nothing around you. There's literally nothing around you. So that's permittivity 0, which is regard to vacuum. Depending on the medium you're in, permittivity is going to be different. Okay. Think about it. Remember to try to relate these things to other, because these are kind of abstract things for us because we can't see them. Think about gravity. So gravity here on Earth is a certain we feel gravity a certain way if we're here, right? And we move a certain way with regards to gravity, right? Because we're in a certain medium, which is air, normal air. But what happens if you are submerged in a swimming pool and you try to run in a swimming pool? It's different because the medium is different and there's an opposition to your movement. Is that an example clear to everybody? So it's not the same to move here than to move in water, right? Because there's a different opposition to the movement, right? Permittivity is the same. if something is electrically charged and generating electrical fields and electrical forces, it's not the same if that charge is in vacuum or if that charge is in some other medium.
Okay, it's going to change now.
It's going to change the interactions.
Yeah.
Correct. And so there's going to be some mediums that allow, we know that there are materials that allow electrical flow, so metals, for example, and then there's going to be other materials that don't allow it. So that's kind of what we're talking about here. That's why it's called permittivity. It's kind of like allowing. It's how much the medium allows the flow of in this case, an electrical field. Okay. And again, kind of relate that when we're talking about mediums, kind of relate that to the environment. Okay, so again, it's not the same for us to be moving here or be moving in water. And so that's Gauss's law. So if I establish a certain surface and I have electrical charges, the flow or the electrical flux that's going to be going into the surface is going to be the charge that's contained within the surface times the permittivity 0, considering that we're in vacuum. There's going to be a couple of bonus activities. I'm just going to mention them now because they're going to be open. Not open. One of them is going to be for, one of them is going to be for this unit. I don't remember if I already gave you this bonus in another course. If so, then you can just bring it up. Did I in any of the other courses give you guys the X-Men movie bonus? X-Men. Well, the X-Men movie came out in the 90s, I think. When did the X-Men movie come out? The first one. I want to see how old you may. I'm hoping that you guys were born maybe around 2000. Because if any of you weren't born yet, then I'm going to be really depressed because 2000.
No,
2004.
2002.
Yes.
The movie came out in 2002.
No, we are from 2000.
You guys were born in 2002.
No, we
Yeah.
did,
2000.
2001.
So this is a movie. This is an ancient movie that came out before you guys were born. Okay, it's like Lord of the Rings. You guys won't know the original Lord of the Rings. You're gonna know the Amazon version of Lord of the Rings, and that is really, really stressful. But I'm not gonna even get into that because I'm gonna get mad. Okay, so X-Men, this old movie that has to do with superheroes that came out in 2000. This is gonna be the bonus, and you can start working on it. I'm gonna open a forum. There's a scene in that movie. The scene is as follows. It's a last part of the scene. They're in the Statue of Liberty. And they're in the Statue of Liberty, and the Statue of Liberty has a sort of sphere part. I think that they're either, I don't know if they're in the head or in the torch. There's some sort of sphere part in the Statue of Liberty where they are at. And so the X-Men, as a reference, because this is like old ancient stuff for you guys. The X-Men are mutants, meaning that they have, well, because I think using the word mutants is politically incorrect now. They have superpowers because their DNA is changed, okay? I think that, I'm not even joking, I think they can't use the word mutants anymore because it's not politically correct. So if they're coming back in the MCU, they're not gonna be called mutants, I think. And so they have superpowers because of that. 3 of the good guys are trapped, are in the Statue of Liberty in this sphere, okay? And then the bad guy is called Magneto, and his superpower is that he controls magnetism, okay? He could be teaching this course. He controls magnetism. And so of the 3 superheroes that are there, one of them is Wolverine, that he's got these metal claws. Adamantium. The other is Cyclops, which is probably one of the most useless one. He's this pretty boy that has his eyes shoot lasers, and for somehow he's the leader of the group, but we don't understand that. And the third one is Storm, and she can control the weather, including thunder. And so what happens is that when they're in there, Magneto grabs some metal and fixes all of them to the wall of the sphere. Are we okay up to this point? If you haven't seen the scene, you're meant. He grabs some metal and he fixes them to the sphere. So they're trapped in the sphere. And this is important for the scene. Magneto is floating. This has to do with the bonus and the electricity magnet. The three good guys are pasted to the metal sphere and they're stuck to it with metal parts. They can't move. Magneto is floating. And suddenly, the pretty boy, the Cyclops, who's the leader of the group, tells Storm, the one that controls the weather, okay, Storm, fry him, or something like that. Meaning, send a thunderbolt to him and hit him. So you knock him out, right? And the answer that Magneto gives is really cool. He says, really? Lightning inside a closed conductor? I thought you guys came from a school because the mutants come from a school. Okay. And so he says that. So really, a lightning bolt inside a closed conductor? I thought you guys came from a school. It would have been really stupid for them to have sent that lightning there. That would have affected them, not Magneto. And there's actually, that isn't science fiction. There's an explanation for that. There's an electricity and magnetism explanation why, if a thunderbolt would have come and hit Magneto, the ones that would have been electrocuted would have been the ones that are stuck to the wall, not Magneto. Okay. So the bonus is for you guys to watch. You don't have to watch the whole movie, watch the scene. And do a little bit of research with regards to what's happening and explain in a one-page essay what's happening. Explain the physical electric principle that's happening there, okay? And I'm gonna open a forum for you guys to turn that in, okay? Okay, that's gonna be that's always a bonus in this course. Questions with that one? It's a very old movie from 2000. I can't believe it that I'm referencing a movie where most of you weren't even born. That is really mind-blowing. It's always going to be one bonus. And the other, this is going to be more for the whole semester, is that I'm going to give you guys the opportunity to pick one of the historical figures of any of the laws that we're going to be seeing here in the course. So it's Coulomb, Gauss, Faraday, Lenz. There's a bunch of people. No. This is a bonus. This isn't, you don't have to do it. Pick one of them. Pick one of them. Research their life and do a telenovela about it. It could be a written telenovela about it. It's a bonus. It's a bonus. It's a house bonus. No, one. Pick one. Pick one. Pick one. That's going to be a bonus. And when I mean do a telenovela, you don't have to act it out. You can just write it out. But well, I actually last year, I'm not going to do that anymore because you guys are also tired about doing videos. But last year, it wasn't a bonus. Each house had 2 historical figures and they had to do a movie about them. And they had to act it out because a lot of the lives of these people are really, really tragic. They're really telenovelas type. They're not happy. None of the scientists that we know about, most of them didn't have happy lives. Okay, they had really tragic lives, and most of them didn't know that they were going to be famous until afterwards. So I'll give you the parameters of that one. That can be up till the end of the course if you want to do it. Okay. It was really interesting. Some of them really did some. And they had to do acting in the pandemic, so it was really cut up. So some of them were in their houses, and they were like, "Oh, we have the baby. The baby is Coulomb," and switch over, and the father was in another setting completely. Some of them did really good acting. Some of them were just downright weird. And that's why I stopped doing this because I think no, well, not too weird, but they told me last semester. Many students mentioned that you guys were really, really tired about professors giving you video assignments. Did that happen with you guys? Just as a,
No.
Yeah, because some of the other students said that the professors were asking them to do a lot of videos and they were really tired about that. So for this course, it's going to be completely optional. If you want to do it, you can do it. And you get points.
And can we do it in houses?
It's going to be in houses actually. Yeah, actually in houses. You can either write the script as a story. Or act it out. If you act it out, you'll get more points. But yeah. Juan Ignacio, go ahead.
You just answered my question. If we act it out, will we get more?
You can get extra points. Yeah, a lot of these were really tragic stories. Particularly read a little bit about, again, I think I mentioned, read a little bit about Tesla and Edison and all the stuff that happened there. I'm hoping I do something and they name a law after me. That would be really fun to have Sosa's law, being taught somewhere. Okay, so what are the application of Gauss's law? I'm going to say it this way because at least that's the way I see it. Gauss's law, the only real application of Gauss's law is that it can help us analyze different situations of objects that are charged to be able to find how the electrical fields behave. So similar to how we did the electrical fields of the three situations, the line, the ring, and the disk, that was one way of doing the analysis. But in those three cases, the things we were analyzing didn't have volume, right? They were linear or surfaces. But now let's say that we're talking about a sphere or a cylinder or something that has volume. Well, that's where Gauss's law is useful with regards to charge distribution. So it could be any of the situations that we see there: a point charge, a sphere, a conducting cylinder, plates. We can use Gauss's law to find those out. And lastly, before we close up, the concept of a Gaussian surface. The way we do the analysis, and next class we're going to do one example of this, a couple of examples of this, is that we define an imaginary surface or enclosure that's a closed enclosure that we're going to be calling a Gaussian surface. This basically is going to be this imaginary thing that if I'm going to analyze a line, or I'm going to analyze a disk or a ring or a sphere or anything, I'm going to imagine that I'm covering that in an imaginary surface that completely encloses it. And so therefore the charge is going to be completely enclosed, and that's going to be helping me for the analysis. And that's what's called a Gaussian surface. And next session, we're going to be doing a couple of examples of finding electrical fields using Gaussian surfaces. Okay, any questions before we break?
No.
Okay.